Darrell Lee Berry Jr. back with some more physics, science. So I'll do some problem solving today. It's been a while since I streamed, so I'll try to be a bit more regular. Part of what brought me back was some feedback I got from a viewer on one of my linear algebra videos. They said it really helped him. He came and joined the Discord. So it motivated me to make some more videos, seeing that some are starting to catch people's eyes and people find them interesting and helpful. So make sure that you drop a line, make a comment, like, subscribe, share, all that good stuff. Join the Discord. Let me know you're interested, and I'll continue to make some more videos. So what we'll do today, I'll do, like I said, some problems. We'll do some thermodynamics today, namely because I have a physics exam, a thermodynamics exam on Wednesday. A bit more background and update on my current academic situation. I'll be graduating from UT Austin with 2 degrees, a bachelor in physics, a bachelor in astronomy, and I'll be going to graduate school in the fall to earn a PhD in physics with an astrophysics focus. In the future, I'll give a reveal video about where I'm going for graduate school and share some about what the research I'll be doing there, which I'll find out about a bit more as we go along, and plan on being a professor in the future. So we'll see how that goes. I'm sure it'll go well. I'm a learning assistant now in a modern physics lab. I think that's changed since the last time I made a video. Maybe remember when it's been. I did upload a video of a talk that I did so many weeks ago. I was at a conference in Maryland for the McNair program, where different McNair participants from around the country came and presented their research. I presented my research on Percepi as recorded my presentation, so you can hear my actual presentation from the talk, and I overlay the audio on the actual slides for the talk, and go through it and change the slides when, you know, this pretty much when I was changing it during the video, even though I think I improved it on a few slides. So that's a bit of background. So we'll go ahead and get to the physics using the Intro to Thermal book. And we'll start with problem 9. So this chapter deals a lot with heat engines, uh, refrigerators. These concepts go into building power plants and things like that. So it says estimate the COP is the what is it? Cost of performance, coefficient of performance of a household air conditioner. Use any reasonable values for the reservoir temperatures. So we have basically uh, the TC, that's the cold environment, in this case the house, and we're going to be taking cold from that. This is basically the AC, and the AC, we're going to have to put work into the AC to make it pull this additional heat, and then we're going to dump this heat outside the house to cool the house down. So we have QH equals QC plus W, which is the heat that's we're dumping outside, is going to be the heat that we're pulling from the inside plus the heat coming from the work from the engine. It says assume reasonable values, so let's let Tc equal 20 degrees Celsius, which is 293 degrees Kelvin on the inside of a house, and let Th equal 35 degrees Celsius, which is about 308 degrees Kelvin. So that'll be our outside reservoir. So when we're dealing with a refrigerator, we know from the first and second law of thermodynamics that the coefficient of performance will be the temperature of the cold reservoir divided by the temperature of the hot reservoir minus the temperature of the cold reservoir. Actually worked this derivation out a bit earlier. Should match. Oh, I'm sorry. This was a engine before. Engine of a ideal gas. So it's a little bit reverse. The refrigerator reverses from the engine. So at this point, all we have to do is plug this in, and I'll go ahead and convert this formula over to math. And I have to change some subscripts. That is TC. This is TH. And at the top, we have TC. So let's see if that looks right. That looks good. So that means that our COP will be 293K divided by 2308, K minus 293K. So it's going to be 293 divided by 15. Give me about 19 and a half. Looks right. So 10 is 200 and 5 is 100 just about. So it's about 300. All right. So this is going to be the max COP. So basically when this is equal, it gives us the max. All right. That seems reasonable enough. And number 4.9. Next, we'll go to 4.13. So this says under many conditions, the rate at which a heat enters many conditions, the rate at which heat enters an air-conditioned building on a hot summer day is proportional to the difference in temperature between inside and outside. So we have a building, we have outside. This is going to be TH. This will be TC. So it stands to reason that the difference in temperature will determine how fast heat flows from one to the other. If heat enters entirely by conduction, this statement will certainly be true. Radiation from direct sunlight would be an exception. Show that under these conditions, the cost of air conditioning should be roughly proportional to the square of the temperature difference. So the difference is TH minus TC. And they're saying that the cost of air conditioning should be roughly proportional to the square of the temperature difference. So cost should be proportional to, uh, let's say it's the square TH minus TC. So this is what I think it's saying. The cost would be roughly proportional to the square. So to be positive, discuss the implication. So let's see what this is. Right, so we have the difference, as I have here, is TH minus TC. And the rate at which this heat will go back and forth. So heat is Q. And when it's going back and forth, it's changing Q. So the, the change in Q over time is Q dot. And have K times change in T. It's proportional to change in T. So it equals some constant times change in T. Actually, I think this whole thing will be squared. Let me just do the proportional again. That's proportional change in T squared. change in Q is that. The heat entering or exiting, well, technically entering, but heat will be going from outward to inward since the difference is so. We call this Qn since we know that heat flows from something hot to something cold. So Qn is the Boltzmann's constant times the change in temperature. Power required by the air conditioner. The air conditioner must remove this heat Q. The air conditioner must remove this heat Q in the work input required. The air conditioner is the Q in that goes in. The air conditioner must remove this to keep the inside at a constant temperature. So this is coming in from the outside, but then it must be put back outside by the air conditioner. And this is going to be the cost that we have from keeping the room at a certain temperature. So you can say work equals Qn divided by the coefficient of performance. See if this works out. So that would be Qn equals work times coefficient of performance. Okay. So if the temperature is going to stay the same, the Qn that's coming in is going to have to be moved out. So this should be Q out equals Qn. It's going to be the same if it's going to be the same temperature. But it's going to have to be the amount of work given the variable of the coefficient of performance. So the change in work equals the change in Qn divided by the coefficient of performance. So that equals a change in T divided by coefficient of performance. Write that. But for a refrigerator, I did write that up here. Thought I wrote it somewhere. This. So I'll write that in. TC over TH minus TC. So it's going to equal K TH minus TC over TC, and that's going to be squared. So that means that the change in work equals the Boltzmann constant change in T squared over TC, which means it is proportional to square root of T squared. Easy enough. Keep on with it. We'll go to 14 next. Actually, hold up. There's something else. We'll discuss the implications, giving a numerical example. So why don't we use the example from before? these temperatures. So that means that the cost is going to be proportional to 308 minus 293 squared, which is equal to 15 squared. The thing about this is, since the units of Kelvin, so these temperatures are in Kelvin, since the units of Kelvin are the width or the length or the size of each degree is the same as Celsius, the difference is the same. So whether I do 15, excuse me, 35 minus 20 equals 15, or 308 minus 293 equals 15, just to give us the same answer using Celsius or Kelvin. So what is 15 squared anyway? To 25. Oh, I wrote this wrong. Yeah, that's the work. So the work is going to be proportional to that. Is the cost. I'm saying that that's a unitless number. So why don't we say we turn our thermostat down? So Tc equals 10 degrees Celsius equals 283 Kelvin. So the change in work is proportional to 308 minus 283, which is now 25 squared. See what 25 squared is. Right. 625. All right. So we're turning our temperature down just 10 degrees Celsius, and we nearly triple the amount of work that's required to do the same amount of cooling. Craziness. Would be the same as if the temperature outside gets a bit hotter. The temperature outside got 10 degrees hotter, the difference would be the same, so the cost would be the same. So if TH equals uh, 318K, and we still wanted to keep it at 20 degrees Celsius, then the increase is the same. So that's why the electric bill goes up so much when it gets hot, uh, because the cost of work that's needed is a whole lot more. So I think that's pretty interesting. So now we're going to 414, a heat pump. A heat pump is an electrical device that heats a building by pumping heat in from the cold outside. In other words, it's the same as a refrigerator, but its purpose is to warm the hot reservoir rather than cool the cold reservoir, even though it does both. Let us define the following standard symbols, all taken to be positive by convention. So we reviewed these symbols already, TH, TC, QH, QC, and W. Temperature on the outside is the hot, because we're It's gonna be temperature inside because we're making the building warmer. Temperature inside is hot, temperature outside is cold. The heat pumped into the building in 1D is hot. The heat, the Q pumped outside is cold. And work is the electrical energy used by the heat pump in 1D. Explain why the coefficient of performance for our heat pump should be defined as QH over W. All right, so let's look at this. So we know that we have our um, cold reservoir and we're taking heat from it. This is the AC. It takes work to do this. We're dropping this heat into the heat reservoir outside. Oh, hold up. Keep thinking about air conditioner. So this is actually, I mean, it works the same, but this will actually be inside. So it'll be outside. So we still have QH equals work plus QC. This is the cost. The heat engine. Then we'll be the work will be going out. So all the arrows will be reversed. So to give you the same thing, if you think about it. Oh, and this is a heater. Thing was reversed. The heat will be coming from the um, inside. So this would be TC over here. Could be the benefit, and then the we'll be dumping heat into the cold reservoir. So all the arrows would be reversed. We'll be gaining work. Now we're gaining heat. So if it was a refrigerator, to be the reversed, and we'll be gaining cool costing QH. But maybe I should wait till I get to that problem. To explain why the coefficient for a heat pump should be defined such. So the cost of performance will be divided by cost. So that will be QH is the benefit and the cost is the work. So the cost of performance is always going to be the benefit versus the cost. What is the relation among QH, QC, and W? What relation among QH, QC, and W is implied by energy conservation alone? So that's this right here. Will energy conservation permit COP to be greater than 1? I don't think so. C. First law of thermodynamics, we get this. And energy is outside. We're adding work. Energy from outside. This is outside. This is side. We're making the hot uh warmer. The work is going to equal QH minus QC. QH is what's being added inside. We're extracting energy from outside. We could get more heat than what we in electric energy we put in. This differently. Q in, this is the heat that's coming in. I guess I should say QC. Well, I already have QC. I'm still trying to think of how to um, maneuver the fact that this can be greater than 1. Taking energy from the outside air, even though it's cooler, it's an infinite reservoir, so there's an infinite amount of heat we can draw. Think about that one. Think about it is, um, ideally, we can take uh, actually, it makes more sense for me to think about it this way. So we look at this. Ideally, if we take 100% of the heat from outside, the engine is also warm. So we have plus something. So this means that QH can be less than W plus QC. So give us a coefficient of performance uh, greater than 1. Solve for W, QH minus QC is less than W, and W is less than QH minus QC. So if W is less than QH minus QC, the cost of performance being QH over W. If W is less than QH minus QC, it's definitely going to be less than QH because QH is bigger than QC. But that means that this can be greater than or equal to 1. So this one it took a little while to move it around to get into a way that makes sense. That could be greater than 1. Use the second law of thermodynamics to derive the upper limit on the COP in terms of temperature alone. So this was a long derivation. So I think I will skip this one for now. Matter of fact, I did this last week on my other channel. Surprised I don't remember it verbatim, but I'll make a note to review it again. And explain why a heat pump is better than an electric furnace. which simply converts the electrical work directly into heat. The idea is that a engine heat from an infinite reservoir to inside. COP can be greater than 1, as we looked at earlier, but a furnace electrical energy to heat, just like how the electrical energy in the light bulb, the filament heats up and then becomes light. COP equals 1, since all of that energy is directly transferred into heat due friction. Well, probably not a total 1, but the maximum it can be is 1. You're not going to get more heat than the electrical energy that you pump into the filament can deliver. Therefore, this is technically going to be less than or equal to 1. Therefore, the heat engine will be efficient. So we used COP equals TH over TH minus TC. And if I use, for instance, the same values from before, did we already do this? No, this was slightly different. Use these same values. We have COP equals 308 K divided by 308 K minus 293 K. So that's going to be 308 divided by 15. And that's going to be a big number. 25 volts. Uh, that's why I divided this before. Yeah, there it is. That was 293 divided by 15 is 308. Well, it'll be actually a bit more. So put it like this, it's definitely going to be greater than 1. Because we can see a heat engine with even a moderate coefficient of performance will outperform a furnace. So awesome, y'all. I will be back later to do some more problems. So I have this many to do. So I'll do a few and then I'll come back and do a few more on stream. So expect me back in just an hour or two. And I'll see y'all then. Be sure to like, subscribe, let me know you're here, and then you'll get more videos. See you next time.